Okay, we're looking at the next section on chapter 1, which is about surds. Previous lesson, we talked about index laws, 1a and 1d. So, as a recap, surd rules really are sort of just an extension of index rules. So, AB, the square root of AB can actually be expressed like this. And as we saw, we distribute that to both parts. So it's actually the same as a half A, a half B. Okay, so surd rules are an extension of this. So the product of two surds is the same as the surd of the product. Okay, and something very similar works with division too. So as a couple of reminders, when we are left with something such as root 3, we say that this is an irrational number. It's irrational because there's no easy way of expressing this as some number divided by another number. Okay, it can't be done. Whereas if we have the square root of 4, for example, well, actually, we can just turn that into 2. And this can be expressed as a fraction. This is a rational number. So this is irrational. This is rational. When we have rational numbers, we often sort of, if we have like root 3 multiplied by 2, we would present it as something like this. Okay, so we tend to put the rational number and then the irrational sort of root afterwards. How do we deal with situations like this? Well, really, these are just products, aren't they? This is just 3 times root 5 times 2 times root 5. So you can effectively shuffle the numbers around, put the 6 together, and then you could multiply the surds. In this case, it's root 5 and root 5, which make 5. So you just get 6 times 5. Okay. What are we doing on this one here? So what's this question actually about? I'm not sure that's quite in the right format. Let's have a look at the next one instead. So root 12 and root 27. Well, the idea is that these are sort of like not like terms, okay? So we want to simplify these down and find if they have something in common. And the way you do that is you find the largest square number that goes into each of them. When you do, you can rewrite it as this instead. So you have 2 of something plus 3 of that same thing. Well, that just means you have 5 of that thing. And lastly, when we have sort of something like this, you may wish to do root 8 and 1 and root 2 and minus 3. And an easy way to sort of do this is with the grid method and to find the 4 pieces that way. Okay, so you'll get root 16 over here, minus 3 root 8 plus root 2 minus 3. Remember that if you can actually turn this simplify this into a rational number like this, then you should do so. The rest of it, we need to simplify the root 2's and simplify the constants, as so. Now, one of the skills that would have been introduced after this is the idea of rationalizing the denominator. So if we have an irrational number, such as root 5, what can we multiply it by such that it becomes rational? Well, squaring it, multiplying it by itself would be an easy way to achieve this. So if we have a fraction like this, and we do not want this irrational number in the denominator, it would be really good if we could multiply it by itself. Now, the problem with that is you can't just take a number that's given to you and multiply it by this, as it changes the value. So the trick that we use is we multiply numbers by 1, where numerator and denominator are the same, because in effect that keeps the value of whatever we were dealing with the same. So that's what we're going to do as follows. You might remember this as an exact value from trigonometry of sine and cos of 45. So some quick worked examples. So lead with the denominator. So 3 root 2. You want to multiply it by root 2, but you need to keep the value the same. Therefore, you need to make sure the value of this fraction is equivalent to 1. So we're going to have 3 root 2 over 2. Nothing to simplify there, means we're done. 6 root 3 multiplied by root 3 over root 3 gives us 6 root 3 over 3. Notice that the top, all of the numerator and all the denominator share a common factor, which is 3. Okay, so that can be eliminated. 7 over root 7. So let's do the same thing again. Okay, gives us what? Gives us 7 root 7 over 7. And of course, there's a cancellation there again, isn't there? Root 7. And finally, what could we do with this one here? Well, shall we concentrate perhaps on the part on the left? So 15 root 5 multiplied by root 5 over root 5. This is only the left part. Would give us 15 root 5 over 5. 15 root 5 over 5 is the same as 3 root 5 plus the root 5 there. There will be 4 of them, won't there? So pause the video, have a quick go at the right-hand side. And the answers are as follows. Okay, notice here that we actually get a rational number as our final answer. What do we do if we have more complex denominators, such as this here? Well, again, we want to try and remove this. We know that the answer has something to do with root 2. However, if we just multiply by root 2, we will be in a situation where this will remove the irrationality. However, I will reintroduce it over here. So I need it to cancel out in another way. And the secret is keeping this the same, keeping the other part here on the right-hand side the same, but changing the sign, okay? As when you expand the brackets, you will get a minus root 2 and a plus root 2, so they will work against each other. Notice that the value of the fraction here is still 1, because it's the same thing in the numerator and the denominator. The multiplication here is a bit more difficult, so my advice would be to do, just as you're starting off, square root of 2 plus 1, square root of 2 minus 1. This here is for the denominator. You might need to do the same when you're multiplying across the numerator too. Okay. After a while, you'll get quite comfortable with it. You'll see that it is the number underneath here, subtract, okay, this number squared as a shortcut. Okay. And then this brings us to our worked examples. So here, we multiply by root 6 plus 2, top and bottom. So I will get, at the top, I will get 3 root 6 plus 6. And the denominator, well, that will give me 6. And then I will take away this thing squared. So it will be 2, for example. Okay. This one's very much the same. This situation, we need to keep this part here. Okay. So we're going to be multiplying by 5 root 2, then the sign change. And then you would do the same for the top. Notice this multiplication here in the numerator is more difficult. So it makes sense to write this out as 3 root 2 plus 4, 5 root 2 plus 7. To do a grid, okay, and work it out that way. We'll get 15, and we'll also get root 2 times root 2. So we'll get 30. We'll get 20 root 2, 21 root 2. They will simplify. 28. And, you can use this to simplify the numerator, the denominator, okay, the same sort of thing as before. applies. So I'm going to get, what will I get? I'll get 25 multiplied by what's underneath, which is 2, so 30, and then I'll get minus 49 for so 30 minus 49 in the denominator. Pause the video, have a quick go at the questions there on the right hand side. Whoops, and there we go, our answers. Okay, so I definitely recommend the grid method for when it's more complex. The key skills, simplifying them. Simplifying each, trying to find a common root between them to simplify. Sometimes we get clues about how we're meant to write a question. So for example, here we would be looking for 3 to be a factor of something. So some sort of multiplication here. And again, the same sort of one on this one. So you might want to pause, have a quick go at this one with a grid. Express with a rational denominator. So this is another signal for rationalize. Rationalize is using the trick of multiplying by 1, or writing 1 in a way such as this. Here, interestingly, if you just have 3 multiplied by, you don't need to multiply the bottom by 3 root 18. You can actually just multiply it by root 18. Or you can do what they've done here, is they've actually simplified before. So often you can do these kind of questions in different orders. So keep, change the sign, and keep. And finally, there's a worded example for you as well. Okay, so you should now be ready to have a go. And the last lesson on this chapter will talk about expanding and factorizing brackets.